Picture this. You've finished a synthesis and everything looks right on paper. Same skeleton, same connectivity, but some hydrogens have been swapped for deuterium. That tiny swap can change how a drug behaves, slow metabolism, or serve as a tracer. Yet proving it requires more than a quick glance. Over the next 10 slides, I'll take you through how NMR, GCMS and LCMS work together to turn that invisible isotope swap into solid, defensible data. Deuterium is hydrogen's heavier cousin, one extra neutron. And that single extra mass unit makes it detectable and useful. Chemists exploit it to track reactions, follow metabolism in biological systems, or tune a drug's pharmacokinetics. But that usefulness depends entirely on being able to verify where the deuteriums are and how many of them are in the molecule. And that's what our analytical toolkit exists to do. Why do people bother with deuteration? Practically, there are 3 big use cases. Tracking reaction pathways to understand mechanism and intermediates. Labelling molecules to study how they break down in biological systems. And improving drug properties. For example, slowing a drug's metabolic breakdown by replacing metabolically labile hydrogens with deuterium. If you're developing a probe or a drug candidate, deuteration becomes both a design choice and an analytical challenge. Here's the core idea. No single technique tells the whole story. NMR tells you where atoms sit in a molecule. Mass spectrometry tells you the weight and isotopic distribution. And chromatography separates mixtures so you're analysing clean species. Think of it like a forensic team. NMR gives us fingerprints, MS gives us the dental records, and chromatography separates the crowd so we can inspect each suspect closely. Use them together and you get a full picture. NMR is usually where we start. In a 1H NMR experiment, a deuterium substituted site often becomes silent. The proton signal disappears or diminishes. That absence is your first clue. To be absolutely certain, run 2H NMR. Here, deuterium speaks directly, and you'll see resonances where protons used to be. In practice, we compare the 1H spectra of the hydrogenated and deuterated samples side by side to spot missing peaks, then confirm with 2H NMR for positional proof. A few practical points from the bench. Always use appropriate deuterated solvents and take care with referencing so chemical shifts are accurate. Partial substitution shows up as broadened or weakened peaks, so don't mistake reduction in intensity for an instrument artifact. Also, be mindful of signal suppression and overlap. Sometimes a missing peak is masked rather than truly gone. When in doubt, acquire both 1H and 2H experiments and keep a non-deuterated standard for comparison. For small, volatile molecules, GCMS is invaluable. The mass spectrometer will show the molecular ion shift you expect. Replace 3 hydrogens and the molecular ion increases by +3 Daltons. Replace 8 and it increases by +8. Gas chromatography separates isotopologues so you can assess isotopic purity and distribution. In short, GCMS tells you whether the mass matches the deuteration level and whether multiple isotopologues are present in the sample. When compounds aren't GC-friendly, polar, large or thermally labile molecules, LCMS is the technique of choice. LC separates your components gently, and MS detects the mass shifts down to 1 Da with high-resolution instruments. Combined with fragmentation data, LC-MS can tell you not just whether deuterium is present, but whether it's retained through processing or metabolism. That makes LC-MS especially useful in drug metabolism studies and when monitoring deuterium retention in biological samples. Let's bring the pieces together with toluene-d₈. NMR shows no 1H signals in the aromatic region, confirming substitution at those sites. 2H NMR shows resonances where those protons used to be. On the MS side, the molecular ion shifts up by +8 Daltons. If toluene's normal molecular ion is MZ92, deuterated toluene shows MZ100, a clear mass confirmation. Together, NMR and MS answer the three critical questions. Is it deuterated? Where is the deuterium? And how complete is the labeling? Before you head to the lab, a few hard-won tips. Always use complementary techniques. Don't trust mass shifts alone to prove positional labeling. Watch out for hydrogen-deuterium exchange during workup or analysis, especially in protic solvents. Keep proper controls. Run the non-deuterated standard side by side. Record both 1H and 2H NMR when you can, and use chromatography to separate isotopologues prior to MS. In short, characterization is what converts a synthesized molecule into an analytically confident one. That's our job as analytical chemists, to make the invisible visible. Thanks for listening.